All right, hello and welcome everybody to the fourth episode of Live Coding with Tanmay and my guest Omer Kamal. Now today we're going to be working on something really interesting. We're going to be implementing something known as a proof of work algorithm, something that is computationally intensive and can be used as a part of blockchain to enable you to know what transactions are valid and which ones aren't, which ones are fraudulent. It's really interesting. It's what goes behind the sort of decentralized nature of blockchain. It's going to be super fun to actually implement and optimize that. We're going to be using two languages, Golang and C, taking a look at the differences between them and what we can do with them too. Now, just so you know, before we do begin, we host this live coding series every Wednesday. So if you do want to be notified whenever we host a new episode, make sure you subscribe to the channel and you go ahead and ring the notification bell. That way you'll be notified on your Google account whenever we start a new episode. And so now, without any further ado, let's go ahead and start. First of all, Omer, welcome. Would you like to introduce yourself?
Hi, my name is Omer Kamal. I work at IBM, and Tammy is one of my colleagues.
Perfect. Thank you. All right, so let's go ahead and begin. Now, by the way, if you have any questions while we're doing this, feel free to put them in the YouTube live chat. We'll go ahead and answer them either as we're coding or towards the end as well. Let's go ahead and begin. Now, first of all, what exactly is a proof of work algorithm? Let's go ahead and take a look at what that means. So what I'm going to do is I'm going to go ahead and share my screen. And essentially what a proof of work algorithm means in this case is that we're going to take something called a hashing algorithm. For example, SHA-256 is one of the standard hashing algorithms that a lot of people use because it's cryptographically secure. And what we're going to do with this SHA-256 algorithm is we're going to feed it some input. So for example, say Tanmay, Bakshi, and Omer Kamal, right? So we're going to feed it some input. And what this hashing algorithm does is it gives us a representation of that input of a constant size. So in this case, SHA-256, as you can imagine, gives us 256 bits of a hash. So that would be 32 bytes that it's going to give us. Now this is represented in hex format, and here's the thing. With a cryptographically secure hashing algorithm like this, you can go from input to output, but you cannot reverse the hashing algorithm. You cannot go from output to input. So for example, it's always possible that two separate inputs result in the same final hash. There can be collisions like this, but because there's 2 to the power 256 possible hashes, the possibilities of that are incredibly low. And so here's the point of a proof of work algorithm. What we're going to do is we're going to take some data and we're going to try to append some random data to it. So for example, something like this. It doesn't really matter. This is literally key smash. So just random data like this. And we're going to try and figure out what that random data needs to be such that we meet some condition with the hash. So for example, that could be that the hash needs to start with a certain number of zeros. So for example, if we start off with like 4 bytes of just consecutive zeros, then that meets our condition and that proves that we've done work on the input to find that random set of bytes. Now, on its own, this doesn't really have much of a use. But when you pair it with other technologies in the sort of blockchain suite of technologies, then this tech actually becomes useful. And what's really interesting is how you can optimize this code to run as fast as possible to actually find those random strings. I'm sure you've known that that like with blockchain and different cryptocurrencies, you can get up to the gigahashes, terahashes, petahashes sometimes with some sort of hardware, and that means you're analyzing, say 1 billion or 100 billion or 1 trillion or 1 quadrillion hashes per second because you need to be able to do those many that quickly in order to actually find the solution in a reasonable amount of time. And whoever finds the solution in the blockchain gets the reward. And so what we're going to be implementing today is the part of this algorithm where we can take some input and find what we need to append to it to make the hash meet some certain condition. We're going to split this up into 2 parts. We're going to start off with a relatively high-level implementation in Go, and so this implementation is going to be focused around sort of the concurrency that Go enables us to have, especially communication across Go routines using channels. And then we're going to transition over to an implementation in C, where I'm going to show you how to implement a paradigm similar to that of Golang within the C language. And then once we've implemented that paradigm, then we'll go ahead and see if we can get C to be faster, and if so, how much effort does that take? And so now, since we're coding in Golang, I'm going to go ahead and hand it over to Omer. He's going to guide us through our Golang implementation. Tell us about our first architecture and what we're thinking. Also, by the way, really quickly, just so you know, we're going to be running this on 2 pieces of hardware today. We're going to be running this on a MacBook Pro, which I'm not sure if LSCP was even a command on Mac. It's not. But basically, this MacBook Pro, pretty reasonable specs. I would say, Omer, you've got 8-core, 16 thread, right?
Yeah.
Great.
You can do htop to see more information.
Oh, can I on Mac?
Yeah, I already installed it.
Okay, that's great. Well, that seems to have got... Oh, there we go. Perfect. It's not frozen anymore. But as you can see, we have a little bit of information about Omer's Mac over here, which is good. And then from there, if we take a look, we've also got another server that we're running on, a power server. This power server over here has 128 threads. And so these 128 threads are going to really help us out with concurrency, and we'll see if we can get that to be faster. Now, power server, whether or not it's faster, that's something that we would need to take a look at. Of course, it's not faster for every use case, but it can be for some, and we'll see. You can actually go ahead and take a look at the LS CPU for power because we're running Linux, and we've got 4 threads per core. But anyway, back to Omer. I'm going to hand it to you. Let's see what we can do with Golang. What do you think our architecture should start off like?
So the very first one, let's just do more of a proof of concept. Everything iterate, so we don't do concurrent. We don't care about threads or anything. So let's just show them just the hashing component and checking if we have enough zeros in the beginning, and then from there we can build up.
Perfect. All right, let's start. So in terms of the hashing algorithm, I'm thinking we use SHA-256 just to keep it consistent across implementations. So let's go ahead and bring that in.
Yeah, let's just input that.
So do we have, I know in Swift we have this thing called CryptoKit.
I need to go see the exact input for it.
Oh, okay. Sure.
1 minute. I believe it's just, you can import SHA-256
While
under
you
crypto.
do that, there is a question that I see in the live chat. And the question is, could you please explain how Swift is going to become the future language? We're not talking about Swift today. Today we're talking about Golang and C. But really quickly, I will say that one of the reasons I believe Swift is going to become a future language is because of the fact that it uses compiler technology that enables it to be relevant for tech like machine learning, enabling it to be high performance, but at the same time, something that developers can code in very easily. And so back to the actual application. So I see that we've got the import for crypto/SHA-256 already set. Let's see. So now that we've got the SHA-256 import, we should be able to create a function for actually hashing an input, which would be an array of bytes. Now, I guess if I were to convert this to a language that I feel like more people would be familiar with, so if we were to take a look at something like this in C, I feel like the function signature would be something along the lines of this. And so a function called hash that takes a string as input, which is represented in Go and C as just an array of characters or an array of bytes, and also returning an array of bytes. Except the return isn't a string, it's the individual actual byte values of the hash.
Okay.
Some 224 or some 256?
I think just some for me.
All right. In the meanwhile, while you go ahead and implement that, I'll implement the part that actually generates the random strings.
Okay.
So if what we're also going to do is create a function called random string. What that's going to do is basically have some sort of character set. Oh, did we just get SHA-256.go?
Are you following what I'm going, or?
I don't think I am, but let's see. I think we should be good to go.
Yeah, it should be good.
All right, so then func random string, we have an array of bytes that it returns. And the way we're going to generate a random string is we're going to take a length, which is just going to be an integer, and we're going to do for I equals 0, I less than the length, I plus plus, have the string, which I'm going to initialize as an array of bytes, which is initially empty, and then I will just do string equals append string, and then we have to somehow choose a random byte, and I'll do that in a second, but then we also need to return that string. Now, in order to choose the random byte, we got to have a random number generator. Now, the thing is, random number generation, when you're doing something like this, can actually be really, really expensive, because every CPU clock cycle counts when you're doing something a trillion or a quadrillion times. And so what I would recommend is that we go ahead and take something, or take a random number generation algorithm that is super, super simple. And so the random number generation algorithm that I've got over here actually runs just 3-bit shifts and gives us a random number. So I'm going to go ahead and get that algorithm out just so we can go ahead and implement that. There we go. So the way we're going to do this is we're going to have a function called random number, which is going to take a seed value, which is going to be an unsigned 64-bit integer. Question for you, Omer. Are integers 32-bit or 64-bit by default in Go? In Swift, they're always 64-bit.
Should always be 64, but you can just define as 64 if you want.
And how do you make an unsigned integer?
You just put U at the beginning.
So uint 64, basically.
Yeah.
Okay. Pretty similar to Swift. That's nice. Okay, so it's also going to return another uint 64, and basically we're just going to do seed equals seed to the left, or seed equals XOR operator x bit shifted to the left, or seed bit shifted to the left by 21 bits, and then seed to the right by 35 bits, and then seed to the left again by 4 bits, and then we just return that seed. And so what this will enable us to do is actually have a random number generator, and what I can do is, inside of the random string function, I can take a seed as well, and I can have this function potentially just return back the new seed after it's been processed. The reason I say that is because every single time we want to generate a new random number, what we do is we actually say seed equals random number seed, so we have the new random number become the next seed, and then in order to calculate the actual random number within a certain bound that we want it to be, we're just going to take the seed and modulo it by the maximum value, which should be 62. Why is it 62, you may ask? It's 62 because our character set is 62 characters long. And so if I go ahead and define the character set, I should just be able to define that as an array of bytes. Now, Omer, correct me if I'm wrong. Can I just do this?
Yeah, you can do that. Run brackets, but one sec.
Like, will it take every character of this string and convert it to a byte in the array?
Yeah, but I'm not sure we can do this as a constant. You have to do this as a variable, but it should work.
Interesting. So what I'm going to do really quickly, just because this logic is kind of puzzling me.
Really?
No, not because the thing is, I don't know Go syntax, because
so
yeah, I mean,
when you convert string into bytes, this is just how you do it.
Oh, yeah?
So it should just work automatically.
Okay, that's good then. But I mean, it can't hurt to actually run it.
Yeah, so let me just fix the error. So we're gonna have.
Well, okay, yeah. Well, the reason that's not going to work is because we need to do.
We can just comment it out.
Set. There.
Okay.
That'll work now.
And then we also need to return that seed.
Yeah.
Okay, let's just switch into.
Go run. And good. Oh wait,
Okay.
what?
What?
Oh, okay.
Oh,
Yeah. Well,
0.
it's printing out a byte, not like a
No,
string.
no, no.
It's printing out
No,
a
but it
byte.
also makes sense because we print out 0 at the very end, which is usually the beginning of the numbers.
What? No, but like the final output is 48, which I believe should be the ASCII code 40, right?
Yeah. No, I was just
Okay.
getting confused because when we look at the number, it sure increase, and I'm like, wait,
Oh, okay.
why is
Yeah.
it why is it less? And then I was like,
Yeah.
okay, it's just a
Yeah.
zero.
Yeah, exactly. Zeros at the end. Yep.
Okay,
Okay. But that makes sense.
so what we
So
can
that's no longer puzzling me. So we should have a random string generator now, and I feel like we should quickly test that out. So if I do a println random string, let's say the length is 20 and a seed is just let's start off with some random seed, and then we'll actually put in like a random number generator that actually uses the time as a seed. But for
but
now, we just want to generate 20.
we also want something just consistent as well right now.
Yeah, exactly.
Let me know when you're
You-
done, and we
You can
can
run that.
be
Oh,
safe.
I think it didn't save. Now it should work. There we go.
Okay,
Nice.
you know
So
what?
we get the new seed, as you can see, a pretty big number because, I mean, it's a random number generator. And then the next thing is just an array of random bytes, basically. But now if we convert that to a string, which, I mean, we would need to do seed and string is this, and then we would do this. But that should now, and we can just turn that to that. And if we run that, here we go. We get a random string every single time. Well, it's the same one because we're using the same seed, but if we were to change the seed, we would get different random numbers.
And then what we can also do now is,
Like
oh, I guess I cannot duplicate the lines. We can check the hash quickly to make sure that it's working.
Sure. And then
And
we'll
then
verify that against some sort of like online hasher that we know works.
Yeah. Do we want to go back into hex, or do we care about it right now?
So
Let's just go into online hashing algorithm right now and just see the first 2 bytes.
all right.
See if
So is this the hash out here?
Yeah, that's
Is
the
down
bytes. 32 bytes.
All right. So if we take a look, what was the string? DPV something. All right. So it's 08 and then 9F. 08 9F.
I don't think it's
0x9F to base 10 is 159. It's right. It's right.
Okay. Is it right?
So yeah. Yep, it is right because the second hex byte is 9F and 0x9F hex to base 10 is 159. And we have 159.
What about the... Oh, okay. So we're going for the second one. Okay.
Yeah. Okay, so our hashing works. That's good. And we only need to process or actually look at the first couple bytes. So I'm thinking just for performance, what we can do is instead of having the hash algorithm of the hash function return the hash, let's actually take a challenge length as an integer, and let's return a boolean. Does Go have a boolean? Yeah, it does. And then just making sure C doesn't. And then we can store that in hash, and then we can just do for I, which is equal to 0, I less than challenge length, I plus plus. We can do if hash I greater than 0, return false, otherwise at the end just return true. So now this hash function should tell us whether or not a certain hash meets the challenge condition.
Okay. So in that case, we gotta find one that can at the moment, and then from there, we can just test if it's actually correct.
Sure, I can find one really quickly. Let's see over here. So
We know the seed, and then we can just have a while loop at the top.
exactly. So I see in Go, while
Yes.
loops are for loops.
Yes, I know. There's no like forever loop, okay? For is just like the
It's
special word for
fine.
everything.
It's fine. Alright. So basically we can just do this. Necessary challenge length is just 2 bytes, so it's a super simple task, or even just 1 byte for now. And then we say if we find this, then break because we found it, and also actually go ahead and print out the string.
Okay. We're also going to change it so we don't go by bytes. We can actually go by bits afterwards. I'll do that.
Sure, later, but for now let's do bytes because that'll be faster because we don't need to convert to bits.
There's a faster way. You don't have to convert to bits.
Oh, you don't?
Like it's very it's not expensive.
Alright, sure. Well, the way that I would do it in C is I would just like run an AND operation with the
A shift.
certain number of bits that I wanted, and then whatever. All
Wait,
right.
wait, wait,
So
wait, 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 wait. How are you gonna do that? Because this is 32 bytes. Like we're talking about a huge number.
I know. So what I would do is, let's just say I wanted to have like 28 zeros. I would just do 24, meaning like the first 3 bytes, and
What
then
if
I
you
would
want 100
take.
zeros?
Okay, well then yeah, that's not gonna work. But
I'm just
then for the last byte, I would run an AND operation for the first number of ones, and then I would just take that and see if it's 0.
Okay.
But anyhow, what we care about right now is that we have the seed. It's saying that seed was declared but not used. Oh, because we're doing this, maybe?
Oh yeah. So let me just quickly fix this then.
Because then string would also need to be declared beforehand, right?
It's string just yeah.
It's just an array of bytes. No, it's an
Oh,
array
it's
of bytes.
bytes. Okay.
Yeah.
Okay.
Okay, so if we run this,
Okay.
oh, it found the solution pretty quickly.
Okay. So what?
Well,
what
it's
does that
only a
even-
single byte, but watch this. If we take this little string here, and if we paste it into this online hasher, the first one should be 0. Yeah, the first byte is 0,
Mhm.
which is great.
Yeah.
Now let's try 3 bytes.
Are you trying to kill my system?
Not exactly.
You should not jump.
There we go, we
wow,
got
that's
it.
pretty fast.
Yeah.
Let's not try
nice.
4, okay?
Okay, let's not try 4, sure. But what that proves is that we have it. Now, one thing to keep in mind is that we didn't take any input. We're just generating random strings. We're not, like, appending it to anything, which is what we need to do for a blockchain. We can't just generate random strings. We have to, like, actually verify blocks, which in this case is just a string of input. So let's go ahead and do that. Let's actually set something called a prefix. And, of course, we wouldn't need the var prefix for that because we could just do, let's just say, oops, no, family backtree, right, so just random string, and Go is going to complain until we put a colon there, and then we can just do hash the string appended, or hash the prefix like this. So basically append the string to the prefix and then hash that is what we're trying to tell Go to do. And so now if we run this should take a lot longer because we're still doing 3 entire bytes of zeros. Oh, never mind, that was pretty fast.
Well,
Alright, so
let's time it because we know exactly how long this should take. Do a
Alright,
thorough
so
comparison, let's build it.
we have that base string, and watch, if I paste in the random string that our little program gave us, we start with a bunch of zeros. Isn't that nice? Okay, now we're not really using what Go is special for right now, concurrency. We'll do that in a second, but right now let's just quickly calculate how many hashes we're actually processing. So let's go ahead and just do hashes.
I'm just gonna input something so we can get at least the right format when we
Sure.
output it.
I mean, right now we're going to be outputting so little that I don't think we really care, but
Okay.
sure.
Oh yeah, true. You're right.
Okay, so now if we time it,
You
it
input
should
time.
print out the solution as well as how many hashes it processed, and if we divide that number by the number of seconds it took, we're currently processing 2.1 million hashes per second, which is honestly not bad.
I was expecting worse.
I was definitely expecting worse. I was expecting sub 1 million, but we got over 2 million, which is really nice.
I'm actually curious. Okay, I need another terminal. Can you run the command again?
Sure.
Is it finished?
It's running.
Yeah, no, so I'm just checking how much of my CPUs are being used. It's not even touching anything.
Yeah, it's not touching it.
Yeah, it's like
I'm sure once we
minuscule.
start multi-threading, we can definitely push your system to the limits.
Yes, that's kind of. I was
It's done
expecting a
in
little
5
bit more.
seconds. Yeah.
I was expecting a little bit more than that. Okay. Uh, is there anything else we have left to do, or should we just start going straight to multi-threading?
I feel let's start multi-threading now.
You know, let's just make sure let's just make sure the output is a little bit nicer with the times and
Alright.
stuff.
Sure.
So we don't need to constantly calculate it like we're using the calculator.
Sure.
To make this a fair comparison, we're gonna time it from the very beginning.
One thing though is that would also take into account the like setup time and stuff.
Yeah,
But that's
well, you
fine.
do want to consider that because in the end of the day, that does matter. Because once we go into multi-threading, if we don't consider setup time, it's not going to be a fair comparison because we might be pre-allocating everything, which at the moment we doing a lot of pans, which does cost a lot because we're constantly creating arrays here. We can do very small optimization here, and it probably does a massive change without even going to concurrent.
Makes sense because if we're processing like this is 13,613,350 hashes, I mean if we're running something almost 14 million times, even like a couple clock cycles saved every iteration, that adds up to a lot of seconds. So
yeah, I just need
sense.
to download a package, get it done,
Yep.
just so we can get like a nice little print.
I'm gonna be really interested to see. Sorry, go ahead.
What do we call it? Hashes.
Hashes.
Okay. I thought we still call it process. Okay. And let's just do a quick
Build
one on
and
this.
then run. Or just run it, yeah.
Yeah, we don't really care about
itself.
build at the moment.
Yeah.
Since we only concern the entry point and the exit, it'll be a
Perfect.
pair comparison. Okay.
Makes sense.
So 2.6.
Perfect. All right, so we got 2.6 million hashes per second. That's, once again, not bad at all. Now, if scaling were perfectly linear on this machine, in theory, we could get 41.6 million hashes per second. But I don't think we're going to reach that limit. Because this times 16, basically, if scaling were linear. But it's not linear.
No, I don't think we're going to hit that.
We have diminishing returns on something like a MacBook Pro because of overheads and stuff.
It's not really that, because right now we're assuming that the system is not going to throttle. I don't have the 60
exactly.
inch, so
that's another
it's
thing
going
to think about. Yeah.
Because right now my laptop is nice and like cool, but as soon as I start using it a little bit more, because that's why I didn't want to go to full bytes. That might actually heat up my laptop.
Yeah, because once your laptop gets heated up, it's going to be bad performance.
Yes, it is. So what we can do is we can take this a slow step, or we jump straight into concurrent, and then from there we build out. Which way do you see it will be better off?
Let's see. What other optimizations do you think we could make right now that would make this faster single-threaded?
So what we can do is right now we can pre-allocate the whole chunks of bytes. And so we can just reuse the same byte, so we don't have to recreate it constantly.
Yes, right now every time we do a random string, yeah, okay. So one thing, let's actually do this sort of optimization incrementally. So I feel like one thing we could do is actually replace this to start off with just make byte len, and then instead of appending, we could just do stri equals this, right? Let's see if that gives us a let's see what kind of performance boost that gives us. Or maybe Go optimizes that out. Who knows?
I don't think that would really make a difference. Okay.
Oh, that actually did make a pretty big difference.
Let's try this then. We got the length, and we also got this. We don't really care about the length really. We can get it if you want, but let's actually pass in the bytes directly.
Yeah, sure. But then how do we know how long those bytes are? Oh, yeah, well, sorry, I'm thinking in C.
I'm sorry, I think you were thinking about C way too much. So we pass a byte and we're going to get it back. And we know exactly the length, so we just need to make it 20 size. So at the very beginning, we can just make that byte.
Yeah, so we can just say random equals. No, not string, random.
Random. Okay. Okay, I will fill in the other one. So sometimes some simple as this might give us a little bit better performance, just because we don't have to deal with the overhead.
All right, so we went from 2.6 million to 3.1 million to 3.3 million. Not bad.
There's even better optimization if you want to do.
Which is?
We're constantly creating one here. So what we can do is we can pass a random string as offset and start from that index.
Let's do that. I was about to say.
Okay, so what we can do here is we also need to add the length of the prefix.
What I'm going to do is I'm going to note down what we started at and how we're incrementing our performance and see how fast we can get at the end.
Yeah, I wonder if Golang you can copy slices. I'm pretty sure you can.
Why would you need to copy the slice?
Okay, we need to set the very beginning to our string. You know what? I'm thinking Ray. Like, I should just think outside the box and do an append.
You know how I would have done this in C?
What? How would you done this in C?
I feel like if we were to just code, C-like code in Go, what I would have done. I mean, you can offset an array, right? Like I can pass an offset to this array.
Yeah.
Okay.
We have to anyways.
Never mind. Okay, then just pass the offset.
So and then we need to also pass the offset.
Oh, that's what I was gonna do. I thought you meant you can actually like increment the pointer of the array ahead by the length of the prefix.
I wish.
Okay,
actually, you might be able to, but I don't want to get into unsafe or something that's not really intentional in Golang.
Okay, well, then I wish we could do that, but whatever, it's fine.
Yeah, we can.
And then we can just do random, and then
we need to also give an offset.
Oh, yeah, you do that actually, and then what I'll do is that in the string we have to add the offset to I, and length of string minus offset.
Why?
What? Why is that wrong? Why is that wrong?
I just equal offset.
Okay, well.
Why do we have to go more difficult?
Alright, sure.
It was such a simple solution.
Alright, I agree. See the difference
let's see how long. I'd be surprised if it's actually less. Ah, 3.8.
Oh, wow, 3.8.
Just as simple as that.
Nice. Okay, so we went from 2.6 to 3.1 to 3.3, now 3.8. Let's keep going. Let's optimize further.
I don't think we can do anything that's left that I can think of to optimize
this. Implementation, you mean?
Yeah.
Well, one thing we could do, I feel like, actually no, the compiler would probably optimize that out, never mind.
Which is?
I was thinking instead of like passing a parameter to random number and then returning it every time and then passing it to random string and returning that, just pass a pointer to random number and it modifies the pointer, and then random string will also take a pointer and not have to return a whole new parameter every time. I'm not sure if that would be faster or slower, because right now this might just be stored in registers to seed, but if we give it a pointer then it would have to be stored in memory, right?
No, because if you get a point, then you have to force the dereference, and then from there you have to. Let's try it.
Let's still try it. I feel like it might. So that means this will have no return value, and we have to like forcefully dereference a bunch of stuff.
I feel like this is gonna cost a lot more overhead.
Yeah, I have a feeling it's going to have more overhead because of memory. Like right now the compiler has the option of just storing it in a register, but I don't think it will after we do this. But let's still see.
I'm very curious.
So am I, actually. And if it doesn't work, we don't need to keep it. So that's the good thing.
And then
so we can just return, give it a... Can we just do this to pass a pointer?
What is the issue now? Oh, yeah.
All right, let's try that out.
I'm pretty sure this is worse, but we will see.
I'm pretty sure this is worse as well, actually.
Okay.
Yeah, it's definitely. Oh,
no,
yeah, it's worse. Let's go back.
It's worse by a slight amount.
Only slightly worse, but it's worse.
You know,
See,
at
when
this moment,
when you try and outsmart the compiler, you're gonna make your work worse. So, never think that you're smarter than the compiler, because you're not.
Okay, let's try this one more time and see what happened.
Okay, we're at 4 million.
Okay.
Nice. Okay.
We didn't optimize. Can we run it one more time? I'm very curious if it just due to frustration.
Sure.
But.
All right, so our peak performance that we measured here is 4.1.
1 minute.
That's nice.
So what we can do now is let's just do a simple thread. So let's just spin up 3 of them and see how fast they can be. And we'll just keep everything in one thread.
What do you mean?
Like we will do the hashing and we will create the random and the hashing in the same a single Go routine. And then from there we can split them off, because I'm not sure if we mentioned this before, but the random itself is probably doesn't take any time compared to actually hashing the bytes. So there's ways to get around that. But I feel like that's probably gonna introduce a lot of more overhead that we don't really need at the moment. So let's do this. So hashes right now is, we need to make this into a list of bytes. I mean a list of ints. And let's make the size like. Do you want to do it that every time we create a thread we append to hash, or do you want to just set the length directly from the beginning?
We're gonna. Wait, what do you mean by that?
So we can pre-allocate the length of the hashes, so we can keep track how much we process them. Do you want to pre-allocate it, or do you want to just append?
Pre-allocate.
Okay. So let's do let's just make another variable number of Go routine. Let's make this let's make it as simple as 2 right now, and then we build off that.
And then we'll see how scaling works.
Yeah. So the very first thing you need to do is just do a loop, and then from the loop we can spin up the threads that require.
Perfect.
I equals 0 plus I.
I'm just gonna see. Swift would have complained here because you have to have equal white space around your operators, but whatever.
Are you kidding me?
I'm not. But
but that's the whole point of IDE, just to do it for you.
Well, the IDE Xcode might help you, sure, but Swift compiler will complain.
Okay. You know, as much as I dislike VS Code when it comes to Go, it sounds better than Swift right now in Xcode.
Come on. It's the compiler's fault, not the IDE's.
Wait, why are we doing now for...
Wait, sorry, not for Go, right?
Yeah, so let me do this first. So
you do it.
What we want to do is we want to create a function, and inside that function, at the very end, I gotta put something. So the function is going to take in, just say the index, because we need to know what index we're going to apply in, and that'll just be int. We will explain this later, and from here we can just pass it in. So what happens is if you use I directly, you're using a pointer to it, and that gets updated very constantly. In this case, we just make a copy and just pass it directly into the index, so you don't by accident get another value that's not there.
Mm-hmm.
And what we can do is we can just copy this in. We will do this better, okay? Tanmay, there's one thing we do need to change.
What?
Oh, there's no way to tell it to stop.
Tell it to stop, yeah, but...
Yeah, we will do that afterwards. So what we need to do is, inside of here, we need to know the index, and we're just going to increase it +1.
Sure.
The next thing is we have a random string, and we don't care about hashes. Secrets. fine. We can just reference that. We can compute this before the loop. Offset.
I will say though that even though Swift complains about the white space, at least it's nice because then it forces you to write good code even if you don't want to. Right? Like you kind of have to write good code. Just like in Python, you have to indent your code properly.
Look, when I was in school, what happened is one of my friend, he copy and paste his code, and this is a multi-server project, so you have to spin up a bunch of systems.
Yeah.
And for some reason, it wasn't indexed correctly, so he was just constantly errors. It was like over 1,000 lines of code, and he's like, what's going on?
What?
He found out when he copy and pasted, the index was incorrect.
Like the indenting?
Yeah. So it just became a pain. It was kind of funny.
Yeah.
Okay, what
are you trying to do with this append?
What do I do? What the heck?
I'm very confused.
I was confused too. I was talking. I wasn't paying attention.
Oh, okay. Yeah.
So we have hashes. Let's also make the seed unique per each instance, and we can just use
the actual index.
Actually, yeah, let's do that for now. Then we can get into more random, just so we have a consistent.
You mean index?
Sorry. Do we have anything else here that we need to worry about?
I don't think so. This is very, very naive, but it should work.
We're not running this.
Work.
We're not running this. This doesn't work. As soon as you run it, it'll stop.
I just realized.
Okay, so the next thing we gotta do is we need a way to tell it that we found a solution. So what we can do is
I'm gonna jump in here and just say, from the little that I know about Go, what I would do is make a channel.
Yes,
that's the
only way. Yes.
All right.
We want to do cross communication, and channels are very safe.
How do you? Wait, what? What's the? I'm forgetting the syntax. You do it.
Do you want to do a channel or do you want to do a pointer? It's up to you. Because in theory we want. Okay.
Let's just do a
channel does add overhead.
Well, we're only sending a solution once. It doesn't matter.
Okay. So
we want to optimize the parts of the code that we hit a lot of times.
Yeah. So right now we don't really care.
No, we actually want this to be array of byte.
Okay. I was gonna just return nothing, just to check how fast it is.
Nah, it's fine. Let's just do
this.
Okay.
And we know the size of this is most will be 1, so we can just set it to 1. So we don't have a like infinite size channel.
Sure.
Okay. And then in here we can. Do you want to just call it solution, or do you want to call it? We should really change it to solution.
Random string doesn't need to return anything now, does it? Yeah, it doesn't.
Yeah,
Random
it doesn't.
At least it doesn't need to return the bytes. It needs to return the seed again, but it doesn't need to return the bytes.
No, it doesn't need, it doesn't need to return the byte. Okay.
Yeah, that's just there for no reason.
Yeah.
See, now that's something that LLVM would have most likely optimized out.
I'm pretty sure this is already optimizing it out. I doubt that. Because the thing is, you pass him back a pointer, and you never really use it.
Yeah, makes sense. Anyway, yeah, this looks good from here, but then we also have to get the actual solution. So let's just do.
No, we have undeclared. Oh yeah, we never used it.
So basically, we're listening on that solution channel, and right as we get a solution, we're gonna continue, and then total hashes processed, we'll set that to 0, and then just do a small for loop. I less than number of go routines, I plus plus, total hashes processed plus equals hashes I. And then we can actually println the solution.
So let's print it out as a string. The one thing I do want to know, Tammy, is are you just really used to doing a for loop, like by index, and not just the for each loop?
Oh yeah, sorry. I've been coding in C so much for the past couple of
Yeah,
days
because
that
because I'm like, okay, it could just be because of the C.
yeah, it's probably just because of the
It
C.
doesn't matter. At the end of the day, I doubt this will make a difference when the compiler look at it.
Yeah, yeah, definitely no. The compiler's gonna
I'll
call
be
this out.
very surprised if this worked, but let's check it out. Because I'm pretty sure we probably had some issue.
Yeah, I mean, if it works on the first try, that
Oh, never mind.
did that work? Wow, that
Yeah,
worked.
that
What?
worked.
Okay, I'm fine with
7.3
that.
million with two
Sure. So
threads
we
only.
went from 4.1 to 7.3 is our current peak. 7.4 is
So
our
we
new peak.
lost. So in theory, we should be able to do 8 million with two threads.
Yeah, but there's a little bit of loss because of initialization overhead and launching threads and the fact that there's two threads going at the same time.
Yeah.
But
So let's do this. Can you run the command? I just want to check if my CPUs are even being used.
sure.
Okay. It's not being touched.
Uh, that's fun.
Yeah, it's not. It's not being touched. You have to. You have to probably stop it. Let me stop it and run it again.
Anyway, it's fine.
Okay.
All right, so once again, quasi-linear speed up here. We're not hitting real linear speed up. But let's actually see what happens when we pump this up even further.
Let's do. I
So
got
4.
16 threads. Okay.
Let's do
Let's
4
go.
for now. I just want to see what it scales up to.
Huh?
Not. Oh, maybe we didn't save the file. Let's run that again.
I'm like,
No, it
what?
actually did not scale very much at all.
Let's do the max 16 then.
All right.
It should at least get into the 10 million. Oh, never mind.
Okay, there we go. That's actually not bad at all. 31 million.
That's pretty good, and I don't think we really need to do any other optimization.
Yeah.
What we can do in theory is we can check how long each of the how long the hash take and how long the conversion take, if you want. Like how long does it take to do the random generator and how long does it take to do the hash?
Calculate that?
Yeah, we can just do a simple this is the total time we spent on this, and this
Since
is
I want to actually, you know what? Sure. Let's do that. Let's profile.
It's gonna be very difficult with multithread. You want to just jump it back down to 1?
Sure, let's drop it back down to 1.
You know, I'm actually curious. Let's make it back to full. I'm pretty sure you didn't save it. There's no way that it will jump that much if it doesn't at least scale a little bit. Yeah, okay.
Oh, okay, yeah, good. Okay.
Oh, actually, that kind of scaled linear at that moment. We went from 7 to...
Almost, but it's not really linear.
Yeah, and then if we
Like
went
if you consider one thread performance, it's not really linear.
Nah.
Like single thread performance was what, 4 million?
Oh,
Multiplied
actually?
by 4 threads, we should have been 16, but we were actually 14.
At 8,
From
on 8
2
is
to
pretty
4
good.
is linear, but 1 to 4 is not.
Yeah. So let's do this actually. Let's make this 128. So what will happen is I can run this completely fine on my laptop. Golang does a very efficient way of storing. Oh, my
But
laptop
it's still a
is
little
heating
bit
up.
slower.
Yeah. So what will happen is since there's a lot of context switching, every thread need to switch out back and forth. And what a channel really is instead of switching the whole thread out with the different contexts, only switch a few of those layers out. And because of that, if you spin up way too many threads, that small overhead does not matter. So you cannot just spin up like a million thread. It will be some performance hit at that moment. There are ways to create, like in Golang, there are ways to lock it to a thread, like lock it to a specific process, but this is only possible in Linux. It is not possible on like Mac or anything else. I'm not sure if C allow you to do on Mac, like you can just pin it to like one code directly, but certain operating system will allow you to do it. Let's compile
Is that
this
like a
to
kernel limitation?
I believe so, because when I was looking into the Golang implementation of this, so what happened is when I implement this earlier and making sure that see if we can pin it to a code and see the performance. Surprisingly, it does pretty bad if you do it yourself.
Anyway, all right, so let's
good.
go ahead and run this on Power now, because we actually have 128 threads that we can run on Power.
Yes.
So let's go ahead and see if we can do that. So while you compile that, and by the way, something about Go that I absolutely love is that you can compile for another architecture or platform from a different architecture. I know you can do that for C too, but it's difficult to install all the libraries and the compilers, but Go just does it for you. It's incredible.
Just for information, as much as I do like it, only x86 allow you to compile for all the operating
seriously?
systems. So they're all small limitations on
but
that.
But still, the fact that you can compile for Power on x86 is pretty fun.
You can also do Z, ARM.
Nice.
I think there's like 20 like architect that Go support. It's crazy. Oh, and you can also build it for Windows, Linux, and Mac, and also other operating systems as well.
That's nice.
It's a lot of variation.
Very nice, very nice. All right, let's go ahead and compile this for Power real quick.
Okay,
Bring it over to our Power server.
Yeah,
and see what our performance is like with 128 Go routines.
Yeah, so the way to do it, you do go arc equal ppc 64 le, and then just go build. If Perfect. I did not mess this up. Oh, I need to do Linux.
Yeah, of course. The day that we get Darwin running on Power is going to be a good day.
That will be a nice day. So to explain in Go arc, just tell you which architect to compile for, and Go OS, just the operating system. So in this case, we run this on a Linux system. So we just need to do the copy. I'll do this off the screen. I need to find
secure copy it over and tell me where it's been secure copied, and I'll actually run it on a bigger terminal so people can actually see the htop command running. Okay. Because in VS Code, I can't see that properly.
You know what? If that's the case, do you want to pump it up to, you know what? Let's just keep it at 3 bytes for now, before we pump it up too high.
Sure. Let me know where you secure copy it to.
Do you want a specific location you want to secure copy it?
Just in the home directory, make a binary called powgo.
Powgo? Okay, sounds good. Okay, powgo.
Got it?
Okay, so pow-go.
Alright, good. Okay. So, oh wait, that's a file, yeah. CDing
it's compiled, man.
Yeah, good. Alright, so if I run that, what I'm also going to do is run htop in another window. So this is showing us all the different, threads that the CPU is running. I go ahead and run this and move over. Let's see. Okay, looks like we're pushing these threads. Oh, and we're done. And how many? 36 million per second. That's not... I feel like when we increase the difficulty and we actually start to process more hashes to make the initialization overhead worth it, then we'll start to see something better. So how about you go ahead and pump that up to 4 bytes?
4 bytes? Okay, let's test this out. Do this again. Okay, let's build it and let's copy it over. Done.
Is it the new binary?
Yeah.
Alright, so we run powgo. Let's take a look at our CPUs. Looks like we're pushing them.
Okay,
now
there
again,
we
wanna be able to use as much of these CPUs as possible. Whenever a CPU's at like 90% utilization or 80%, that's a bad thing. We want them to always all be at 100%.
So
making sure we're saturating all of the processors.
I think one of the reasons why we at one of the CPUs always less than 100 could be that one CPU or that one thread at that moment is doing a hashing. Like, I mean, generating a random number, since that's not really CPU intensive at all.
Makes sense. Yeah, that has more latency than it does compute.
I believe so. Yeah, it should, because you're sending up variables and stuff.
I feel like 4 bytes is a bit too difficult for it right now.
Let me change the hashing to another version, so we can do it by the bits.
Oh, I think it's done.
Oh, okay.
Oh, 37 million. Not much better than your max 40 million. Although we did process just under 2 billion hashes in total this time, so that was nice.
Yeah, that's pretty nice. We did hit... Can you... I believe there's a binary here, pow, unless... that's on another server.
Oh wait, no, sorry, I was confused. Your Mac never hit 40 million. Sorry, I was confused. But your Mac hit at a peak 31 million,
Yeah.
and Power Server 37 million. So not bad, but definitely not the scaling we were hoping for.
But we also gotta keep in mind that the CPU's clock cycle does make kind of a difference. Because if I
Yeah.
pump this down back to 1, you will see that it's not really a fair comparison.
Yeah, that makes
So-
sense to me, but I want to be able to optimize this such that on a system with so many threads, we actually get it to work well.
Yeah.
So I feel
So
like
let's do this.
Yeah.
I dropped down the threads to back, like the go between back to 1 and the challenge to 3. Let's just see a baseline of how much 1 of the CPU
Power
can handle.
Thread can do. All
Yeah.
right.
And
Now,
we
if
do,
we had access to a bare metal power, I would have like changed the SMT settings to see if we can give more resources to a single thread, but we don't have access to a bare
Yes.
metal right now.
we also do need to keep in mind that we're doing SMT full on this system. So each core actually have 4 threads, which is kind of overkill sometimes. But we'll see.
I feel like for
Can
like
you?
a database, that would be good.
Yeah. Can we run this? Can you run the command again?
Sure. Have you changed the binary?
Yeah. I just want to. It should not. It should only touch 1.
It's maxed out as single thread.
Yeah, that's the intent. I just want to see a baseline of 1.
You changed it to 3, right?
Yeah. It should
we
be
can't
done
We can't handle like
a billion.
4 on
No,
a single
but
thread.
I'm pretty sure 1 should be done by now. Oh, it could be like a 1 million per second on the system, if anything.
It's probably either a million or sub. It's definitely not above a million per second.
Let me double check how on my system how long it should take.
Yeah, that does not look like it's gonna stop soon.
Yeah, this does not look like. Oh, because the hashing was different. Let me pass it a 2 in the beginning.
Yeah.
1 sec. Let me see if I compile again. How long does it take to compile?
Sure. Should I stop this?
Yeah, stop it. Yeah, this is not good.
Tell me when to run it again.
Okay, so what I'm gonna do is I'm gonna make the challenge like very simple. At
How
2.
many bytes?
2.
2? Sure.
Should be very fast to be honest at that moment. But let me test it on my laptop to see how many. Okay. Oh no, this is a very fast baseline if I give you this.
How many hashes are you getting?
22 on 1. This one is a very fast baseline if I give you that.
But you have 12 go routines going though.
Oh, do I?
Yeah. Which kind of explains why you're doing 20 million.
I thought I changed it to 1. Do you
No.
change it?
No, I didn't change anything. Come on.
Okay. That will probably explain why I was getting such a high number there. Okay, now this makes a little bit more sense. For 2, I need to process about 100-ish. So it should take about...
100 million?
I hope it's not 100 million. Okay, let's make the challenge 1, okay? This is
Why
way
is this
too hard.
taking so long?
Because our random seed, it just probably got unlucky.
Yeah.
Because we're given a... Wait.
You know that this random number generator doesn't work with zeros, right?
Yeah, I know. We said at 1, 0. No, that makes sense. Oh, wait.
Yeah, this random number generator needs a seed greater than or greater than 0. That means the first go routine wasn't ever doing anything.
That's actually bad. Yeah, that is true. Let's see. You know, to make this less of a pain, let's change this to 2 and let's just +1 here.
Yeah, sure. Perfect. Okay. Run that. That explains why our power server wasn't doing anything. Alright, now compile this for power and send it over to me. Let's get a single thread baseline.
Okay. Done.
Great. Oh, that was quick. Approximately 2.2 mil per second.
So let me do this. Let me change it to 4. And we should probably... let's see how it scale up.
Sure.
Okay, let me just type in the bell command again.
Did you change to 4?
Yeah, change to 4.
Okay.
Okay, let's go.
Oops. All right, so run. Okay.
Yeah,
Not
it doesn't really
great.
scale. It doesn't
And
scale
probably
at all.
because the challenge is so simple that the scaling doesn't need to happen.
Okay, I'm gonna change it back to 3 and see what happens.
Sure.
It could also mean that what's happening is that we don't really consider too much either. What I mean by that is that the threads might be hopping around too much, as I now idle to like 1 or 2. But we can test that with htop.
Yeah. Okay, have you secure copied it?
Yeah.
All right. Let's see. Yeah, looks like we're pushing 4 threads. Oh, and it's done, and we got 9.7 mil.
That's
Not too bad.
You know what? Let's just bump it back to 128 and see what happens.
Like 2.7 million, which was our previous peak, times 4. We would have expected 10.8 million per second, but 9.7 isn't too bad.
Yeah, so let's do this. I bumped it up to using everything. So let's test it out again.
Like 128 again?
Yeah.
Okay.
It's busy. Are you running it by any chance?
Yeah, I am, but it's only... Oh, okay, yeah. I'm no longer running it.
Okay.
Someone's asking, where are we using PowerPC architecture? There are a couple of different platforms that support the PowerPC architecture. As you mentioned, one of them is IBM Cloud. Sorry, did you secure copy the new binary?
Yeah.
All right, let's see. So let's see if we're pushing. Oh wow, yeah, we are pushing all the threads. Definitely not as much as I wanted to, but 36 million per second.
I don't think I even use anything. Let's bump it up back into challenge to before.
Yeah.
And let's see.
Have you secure copied it?
Oh, I didn't even build it.
So challenge is 4 and threads are 128.
Yeah. Okay, let's go.
Okay. Yep, looks like we're pushing our threads again.
And it looks like they're mostly being used now.
So look, here's the thing. We want to be able to saturate the CPUs even more so they're not just stalling sometimes, like you can see they are right now.
Mm-hmm.
And to prevent that from happening, an optimization that you came up with, actually, is to have a bunch of Go routines generating random strings, and then have other Go routines dedicated to hashing them and checking them. So do we want to try implementing that later?
Let's do this. I'm gonna copy another version of this, and we're just gonna test if it works.
Yeah.
Um.
Okay, I feel like 4 is too challenging for the server. Well, it's not too challenging. We'll hit it before 2 billion. We proved that last time.
Okay, let's do this then. I'm gonna change the hashing, so we do by bits and not by bytes anymore. Okay. Let me change the hashing algorithm. So this is a hashing algorithm I came up with last time with. I'm just gonna update it so it matches what we need.
Mm-hmm.
So the input is data bytes challenge length. Okay. Hash, and then everything else should be fine. Changes to. Okay. So the difference that what we want to do is each of the bytes we know is 8, and then from that we can check if the first few bytes are 0, and from that at the last index check if the last bit are 0, like the very first the beginning of the bytes when we convert it, and we can do that with just bitvisor operation.
Sure. All right.
So at this moment, what we can do is, did we name this hash? Oh, supposed to be name hash. Okay. And let's change this to be, let's do 20. Let's do 27. I'm just feeling lucky. Let's compile this and send it back to the server and see how long that should take.
Okay. Let's see. What's our performance looking like? Again, we are almost maxing out our CPUs, but I feel like if we have the separate threads for generation, separate threads for hashing, we'll push it even further.
Yeah.
36 million per second.
Okay. So let's get into the object where we have different stuff doing different items. So the very first thing we want to do is that let's split the relationship. So for every for every one generator, let's have 2 or 3 the hash with it or something like that. And we'll be calling a function to that and let that deal with the complex stuff inside. So the very first thing we want to do is let's define a function and let's do this. The way I defined it in my other example was pow on call, because it was able to go directly on one single call if we want it, or one single thread. We're just going to keep the naming convention, and then from there we can change it up. And then this doesn't return anything. And the only thing that this requires is that we need to know the data. So what is the input? What is the number of generation? What is the number of hashing we want?
Wait a minute, just hold on there.
We can remove some of the stuff.
One sec. You just put something in here that's completely alien, and you just glossed over it like it's nothing. What's this syntax over here?
Which one? That?
You didn't specify the type for this parameter.
I did, which is int.
Wow. All right, go ahead.
Wait. Swift doesn't have that?
Nope.
Have you done Java?
Does Java support that?
Yeah, I'm pretty sure Java support that. Whatever. I'll make it nicer for you and actually put int. But what happens is it will always assume the next one. If that doesn't happen, it will go to next. We don't care about the codes anymore, and then we need to know the channels.
Yeah.
So what we're gonna do is we're just gonna take this as a little example and paste it here. There's gonna be a lot of work just for this one little test. So the very first thing we want is we wanna create the bytes. And what we wanna do is we don't wanna copy anything, we wanna pre-allocate the whole chunk. And the reason we do this is we saw before that when we pass bytes back and forth or copy it, that we actually have a huge performance hit. So what we wanna do is the random generator, that will push a number into a channel, and then all the hashes will listen to that channel, and it will return an index. And the index is inside a massive chunk of memory for a block of, say, random numbers or a block of something. So the very first thing we want to do is define how many blocks each of the random generator and the hash is going to process in one shot. So we're going to just call it block size, and let's just make it as simple as 1028. We can play around with this number to see if it's better.
1028.
Yeah, it's just a random number.
It's supposed to be 1024.
No, 28, okay.
Come on.
Okay.
Well, that sounded off for a second. Anyway, go ahead.
Okay, you're too used to 1024, okay?
Yeah.
So the next thing is that we want to start spinning up the threads, but before we get that, we need to pre-allocate everything. Now, before we do that, is how many, what's the size of the buffer that we want to have? We know that creating the random numbers are probably, I don't know, maybe 1% of the cost. I don't think it's going to cost too much. I think the actual cost is going to come from that hashing. So we can just assume
profiling in C, and it's usually like 0.1%.
Yeah. So what we can assume is that we just need a buffer of maybe 2x of how many number generator there is. Just one moment. And then what we can do from there is let's slowly build that chunk. So we want a byte. So let's do. Let me see what I called it before. One moment. Okay. So I'm gonna create 2 channels. So one of the channel is the on process, and the other channel is gonna be process. And each of those will just have an int. And in this case, we want the size just to equal to the number of hashes times 2. This, so we have a buffer of 2x. And what will happen is when we generate the hashes, we will pass the index into the process index. The on process index. The hash will pick that up, and once it processes, we will pass it back into the process index, and it will go back and forth. So the random generator will always keep it nice and fresh.
Makes sense.
So for this to go, I'm just gonna assume that this is 1, just for to make this simple, and then we can spin up threads afterwards. So we can just assume a function being called in the background. And then what we're gonna do, sorry, I need to pre-allocate the size first. So the size is gonna be, yes.
Yeah, there's a comment. Channels are another great feature in Go. I agree, they're an amazing feature, but they're even better if we could implement them in C. So we'll get to that in a bit. But go ahead.
We kind of have to implement it in C to get to get a similar architect. Yeah. So I'm gonna have something called blocks, and it's gonna be a triple array of bytes. The main reason is that we are dealing. The first one is the buffer. The second one is the chunk of blocks, and the last one is actually going to be the string of randomness. For this to work, we need to allocate everything. And to allocate stuff, it's going to be kind of annoying, so we have to kind of brute force everything. So we're just going to do 2 simple for loops. The first for loop, we'll just create it. The second, and then we will pop it into the unprocessed index. And then we also have to pre-allocate each of the chunks. Inside of that, we want to allocate how long the hash is. In this case, this is incorrect because our architect that we currently do right now is slightly different. So we also have to take that into account. So the very first thing we want to do here, based on what we did here, is let's get we're just gonna assume 20 is a random string we're gonna add. We can make this module later. So we want to make a block size of 20, but before we continue, we want to make sure that we append the string. In this case, we can just pass in not a string here, but a byte, since that's what we've been working with the whole time. And we can append this at the very beginning. It's gonna be a little bit ugly, but whatever.
It's fine.
It's only ever gonna be 1-1, so like I don't really, well, once per like call. Now the next one is we gotta generate each of the random numbers. For this, we can just do as simple as, let's create a random generator. So we just need a seed. In this case, we're just gonna take time. So the reason why I want to do this now is because it's not as easy as before to just index it by 1, 2, or 3, because we never get that value passed down to this far. So we're just gonna take the time. This might make it a little bit harder to track, because since the seed is not consistent, we don't know how long each compute should take. So we can go anywhere from like a few seconds to a couple of seconds. It just depends on what seed we get lucky with at that time. So now if I look at the rest of the algorithm here, what we want to do is we need to do a constantly for loop. And this for loop, we just constantly look for index that we can use. So in this case, what we want to do is we want to get a block index back from the on process. And then from this, we want to fill up everything with a new random number. So for that, what we can do is we can look at how we create the random strings here. And we also need the offset. So let's get this into our code. Okay. I wonder if I can, because the thing is, since we're passing like a list right away, we might be able to do something else with this. But before I continue, let's do this first. Did I misspell something? Okay. do keep in mind there is one thing that we really neglect. I'm not sure if you catch it, Tammy, yet, is that we don't check if we actually finish. We just assume that once Golang exit, then all the threads should stop.
Yeah, so that's definitely not best practice. It's not production ready code.
We never say it was
But
production.
it's fine for now.
Yeah. Wait, why is this not working now? Floxy. Does time not give you a... Well, man, I thought time should give you the Unix code. Maybe it's different. Oh. This is actually another command. Unix. Let's do nano and on and 64. Okay. So what we're gonna do now is we're gonna loop over each of the blocks, and we can just do a simple for each loop. And we can just give it the index like directly. So the difference between loop and Go is that there's two for each loop. By default, the very first one is always going to be the index. If you want the value, you just got to put another variable here, and then the value will get filled up here.
Which is weird. You would think it would be value by default.
No, it's not. I found it weird at the beginning, but it is pretty useful in this example because we don't really have to care about it as much. And then once this is done, we need to pop it back into the process list so that something can listen to it. So we can just do a simple process index and then input the block index. So this will take care of creating the randomness. The next thing we want to do is we want to actually process the hash. In this case, we do want to make a for loop so that we are able to process it correctly. To terminate the background process. Okay, we do have a question.
Do we? Terminate the background workers first to terminate. Yeah. Yeah, we understand, but we don't want to implement the graceful shutdown right now because that would take extra time, and right now we want to quickly be done with Go so that we can go over to C and finish that implementation as well and have a little comparison of performance. Yeah. But overall, though, we do understand what you're saying, and in real code, you would implement a graceful shutdown.
Yeah. So what I can do is I can just copy another version of this and just fix it up to match what we have, or we can do it from source. It doesn't really matter. It shouldn't take too long just to write the rest out.
Sure, we can quickly write it out.
Yeah, so let's just do a quick run. I equal 0. I forgot something.
What?
The process hash. It's gonna be annoying to deal with.
What like process hash?
So we need to add how much we hash, right? And that's gonna be a little bit tricky because the index itself is gonna be unknown. So like the way that we keep track of how much we hash is kind of naive. That we're assuming that each thread will have their own dedicated one. What we can do is we can still do a naive approach right now, just to get this like finished with. But we should really fix it in the next live stream. All
right, sure.
And then I++. Let's quickly do this. Hold on.
So by the way, everybody, just so you know, after today's live stream, later there will also be a recorded video on how to do something similar on GPU. So what we're doing right now on CPU is really nice, but it's a task that is really, really meant for something like a GPU because we're not doing anything super complex, but at the same time, we can really accelerate this by doing thousands of things at once instead of hundreds. And so I will be showing you how to do like multi-GPU code with CUDA in a recorded video later. And then next week's live stream is going to be really interesting. It's going to be expanding upon this and doing something super fun. So make sure you stay tuned for that. Yeah, so another comment that you can go ahead and continue to implement, Omer,
Okay.
but another comment that I see is that C multi-threading implementation is going to be interesting because C uses OS threads, whereas Go uses lightweight multiplex threads. Yes, that will definitely be very interesting because we got to see the current tasks that we're running. Does Go's lightweight thread really add to the performance in this case? That's debatable. So for example, if we take a look at these lightweight threads, they're really good for things like web servers because of the way that web servers work, because you would have like thousands of requests, and if you have hundreds of threads, they can all keep context switching with very low cost. But the thing is, with something like this, you have a constant number of threads that you're running. The extra Go routine, like the Go runtime, it's not we don't know if it's necessary. So we'll see if that's something that helps or actually reduces performance. We'll check that out.
Yeah, I don't think it'll matter too much.
I think because of the way this task works, we're not going to see any extra overhead or less overhead compared to OS threads.
Yeah, I feel like it's just gonna be very similar. Like,
yeah, it's gonna be.
It is a very lightweight overall.
Yep.
Okay, solution. We want pass back. Okay. Is the solution? Oh, I messed up.
What's wrong?
So I was assuming that we have a channel with string, but I think we define it as byte. So you just gotta pass it back as a byte.
Yeah.
Which is easier for me. Okay. Now I think I have one last error to deal with. Oh. Wait, how do we define channel up there? Oh, no. Do you see anything wrong with my implementation of channel?
You have an extra square bracket at the end there.
Oh, sorry, I didn't see. I was kind of blind to that.
No worries.
And we have a lot of issues. Let's deal with this. Offset is gonna be, we're gonna call this prefix. Prefix. Oh, I caught the one function there. Hash. And we don't care about that. This is what happens when you just copy and paste the one above it.
Yeah.
And we want to test 27 just for now, just do something very fast. And then it return a boolean, so a hash. And let's not constantly recreate that boolean.
Once again, Swift would have optimized that out.
I'm 100% certain this will be optimized, but I just want to make sure.
Sure.
We don't care about the seed here anymore. That doesn't matter anymore. Okay, what else is left? Oh, okay. So all of this can just be deleted now.
Essentially, yeah, should be able to.
Okay.
All right. Do you think your code is ready to compile?
It's ready to compile, but it's not going to do anything. So here's the problem. Right now, we're not keeping track of any index. Like, which index should we actually subprocess, like add in the hashes to everything. So what we can do in theory at the moment is just give it an offset, and then from there, just like insert it.
But that's what we're doing already, right? We have the offset.
Offset index. No. So what I mean by this is I'll explain afterwards.
Sure.
Hey, actually?
Yeah, I don't think we need that.
No, we don't. No, but the thing is, we're not keeping how many hashes we actually been doing.
Oh,
right now,
how many hashes? Oh, okay, yeah.
Yeah, so I'm trying to think of a way that we can do it without causing too much issues. And since we spin up a lot of threads, we cannot even update the same one anymore. Let me just
I feel like I
check.
can. Let me do that 1 sec. I feel like I can figure out a way. Hashes. Then we can do. Where exactly are we? Or actually no. Hashes pointer to integer.
Oh no, it doesn't matter. What we can do is.
1 sec.
Okay, I got it. Well, I know what we can do now.
Sure.
Oh, we're gonna go overcomplicated.
What? Oh, you don't want to do it that way?
We have to kind of undo one of our assumptions, and that's it.
Which was?
So the very first thing is that we pre-allocate the hash size, right? In this case, let's not pre-allocate it, and let's just make it empty, like empty int. Okay. Now what we can do is, first of all, we can just remove all this because this is not needed anymore, other than solution.
Mm-hmm.
Do we care about this stuff here? Yes, we do. And then we also pass in. Oh, we don't have to do anything there. So what happened is, since everything is being done as a loop, we can just assume that your index that you insert into is going to be the length of the hash, right?
Mm-hmm.
And then we're also gonna append one to it. You got it?
Okay.
So hash is going to be append. What we can do is just the hash itself, and then 0. So the reason why we don't do the other way around is that the first index should be 0, and what will happen is that when you take a length of like 1, you're gonna get 1. You're not gonna get 0. So we might as well just do get the length first, so we don't have to minus 1 at the end.
Mm-hmm.
So now we also need to pass in hash index. Again, it doesn't have to be. It's probably not correct. Now the good thing about this is that when we add it to whatever the index is supposed to be, you just only need to plus equal block size, which is a known size. So if we run, say, one of these, so we expect the prefix to be whatever that is. We expect 1 generation. We want, say, 1 hashing and the solution channel. Okay. Let's test what happened and see if it works.
I'm hoping it will. It
and
looks like you have an error.
syntax.
13, line 13.
Oh,
Hashes.
got it. Wait, what?
No, it was line 13.
Follow index. Oh. Let me see. Undefined hash. Nice.
What should that be?
Hashes.
Yeah, okay.
And oh my god, this is gonna be. Oh. Oh, not this. Let me see how to fix it. So what happened is that they assume that nothing is there and everything is dead.
Okay, that's because you're not inserting into the unprocessed index by default, right?
Am I not?
Oh wait, no, you are. You are.
I thought about, okay. So when I initialize everything, I'm inserting. Okay, let's quickly go over this. So for every block, I insert the ID. That will initialize it.
Mm-hmm.
And then in the go, I get the unprocessed index. And then I process it, and then I push it back into the process. And then in the next one, I get the process index. And I don't push it. You don't push it
back.
Yes, I don't push it back. The for loop and right there. So let's push it back. On process index. What do we want to push back? Block index. Okay. Oh, it didn't break. I'm actually happy. But the challenge might be a
Well,
little
it
too
did
much.
now. Oh, never mind. It actually gave us the solution, but it crashed after the solution was given.
Line 27. What is line 27? Ah, yeah. This makes sense. Is our assumption. Tammy,
Mm-hmm.
this is why I don't. This is why I don't like.
That is funny.
Ah. Yep. And then we can just add the value directly. We don't care. Yep. And this value is never used. Yeah, we don't care about that at the moment. Okay, let's see how long this take. We probably assume since we only using a few threads, it shouldn't take too long. It will probably take a while. Let me just double check how much CPUs I'm using. Yeah, I'm barely touching anything, so it's gonna take some time.
What's our solution? Did we get a solution yet?
No, not yet. So
How
let
many
me
seconds
just
would you estimate we take?
let me just
What's our
pump this
what's our
out.
difficulty? Sure.
Oh, difficulty 27
Sure.
bits.
So the number of hashers right now is 16, right?
Yeah, I'm just
And
gonna.
the number of generators per hasher is 16 as well.
No, it's 1. 1 to 60.
Sure. So total hashers, total generators 16. Total hashers.
There we go. 13 million per second. I feel like this is slower.
This is slower on your Mac, but it'll probably be faster on Power.
Because we went from 30 million from a very simple example to this. But
Yeah.
what will happen if we do this? For I equals 0, I plus plus, let's say less than 10, I plus plus.
So you're saying make it so each group has their own local generators.
Yeah, so what happened is we pre-allocated way too much memory. And since it probably have to do a lot of context switching from different CPUs to access that, which probably hit the performance. Yeah, so I need to do, let's do for every one we spin up, we do 3 hashes.
Sure.
Is I plus plus incorrect?
Shouldn't be.
Oh. I knew I did something wrong. It'd be kind of fun. Okay, there we go. Much better job.
Oh, wow. That's nice.
So let's pump this up to, so how many cores do we have on the CPU? 128, right?
128, yeah.
Yeah. So what we can do is we can just do 128 divided by 3. And we can just do, okay, let's do 43 since that's not really a number.
Yeah.
Let's do 43 here.
Yeah.
So we will have 43
let's
generator.
go on the safe side. Let's do 42.
Okay. So what will happen is we should be able to saturate everything on it now.
Yeah. Okay, so what you're saying is for every one generator, we have 3 hashers working.
Yeah.
Okay.
And I put it
try
onto
this
your
out.
power server.
It's up. All right, running. Let's see if we saturate our CPUs. Oh, it was done super quickly. Wow. Yeah, we need
Do it,
more
no,
of a
do it again,
challenge.
do it again,
But
do it
we're
again,
at
do it again.
70 million per second though, which is way better than we were before.
Okay, this is way too fast.
Yeah, we need a much more difficult challenge.
Let's go into, what do you want to do 32?
Yeah, let's go 32.
No, let's go 29. Let's just slowly go up before we go too high. Because every little bit does add a lot of time.
Yeah, you're right. It's exponential increase. Yeah, that was super, super quick. That was essentially no difference.
Okay,
Or never mind, I just didn't update.
No,
Okay, it looks like we're saturating our CPUs pretty nicely.
a little bit better than before, but I still see, no, not as much. Let's do this.
Not perfect.
Let's go on the, let's go a little bit crazy and do a little bit more.
99 million per second, not bad at all.
Yeah, let's just do 50.
Okay.
In theory, Golang
50
should be
what?
able to handle this. Go. I want to see
Alright.
this. I'm very curious now. Okay.
Oh, that was quick. 97
again.
million. Do it again, yeah.
So, you know what I found the funniest?
What?
We optimized it faster than what we did before.
Yes, it is. Okay, 99 million. Okay, we're
So-
capping out at 99.
Yeah. So the one question I did have, when you work on the C component, did we ever hit this fast?
No, we did not actually. I will be interested to see if we can
So-
now.
I think what we have to do is we gotta maybe follow the exact same autotech
Yeah,
path, right?
exactly. Follow the
So-
exact same logic.
I think that's probably the reason why we.
Oh, we hit 100 million. Hooray.
So just for a little bit more background information for people on the call, the fastest that we hit before was 50 or 60.
Yeah.
So hitting us 100 million for just a small change. Because I know
It's
that
pretty
I know what small change actually happened. So what we did before was that when we appended the strings, I mean when we do in the random generation, we give it a block and then we also append the prefix to it. And that caused a lot of overhead apparently. Since we pre-allocate everything now, it should look better.
Yep.
Okay, let's do
Alright.
this in C now.
Let's do it in C. All right, finally, now it's time for C. Let's see if we can get this to go faster than just 100 million per second with C. So I feel like the first challenge that we're going to encounter is actually implementing channels in C. So let's go ahead and do that quickly. So we're not going to implement exactly channels from Go in C, but we're going to implement something reminiscent of Go channels. So first of all, I'm going to do a little linked list struct, linked list node, and just because C is going to complain, we have to do type def, or actually just struct and then type def structs.
So we do have a question. Someone asked how much does electric compute 128 code cost per hour?
Yeah.
So I'm guessing how much does just a typical power server cost, since those are the only servers that we really have.
Well, no,
many-
Intel can get up to 140, I believe,
Oh, I
with
didn't
the
know that.
Cascade Lake.
Okay, so they increased. I thought they will cap out like at 100 or something. Then I know it was 140 now. Okay, that's good. Yeah. So tell me, how much does it cost per hour?
You can calculate that while I implement this.
Let me actually. No, I think it's about. It'll probably be similar to GPU wise, because this one system is kind of unfair. I believe there's 4 GPUs also.
Yeah.
So it'll be probably hard to estimate, but it could be maybe $1 or $2 an hour. But the GPUs itself does add a lot of expense to it.
Yeah. Linked list node. Next. Okay, so we're gonna have this little linked list structure, and I'm gonna.
You know what's so funny?
What?
I can probably optimize this already.
What?
So what happened is, I think it was like 4 or 5 years ago.
Yeah.
I was doing something and I was using just a regular linked list, and this is in Java, so I cannot clear out my memory correctly fast enough. Right?
Yeah.
So I was creating so much nodes, and also removing it so fast that my memory went from like a couple hundreds to gigs, to tens of gigs, like 8-9 gigs.
Because the garbage collector wasn't handling it properly?
It wasn't fast enough.
I see.
So what I did is, I'm like, okay, let me just make an index and just route like just circle. So if I hit the end, just circle right back to the beginning and constantly go, because I know the size of my linked list eventually.
Yeah.
I went from having like almost 10 gigs down to like 100 megabytes. Because that one thing
I
was
think you
spending
told
so
me
much.
that once before. That's pretty incredible.
And the thing here is, what was gonna happen if you keep allocating new memory, like you allocate memory constantly now, right? Even though the overhead is a little bit less than doing every single time, since we do stuff in blocks, it might affect it afterwards, because every call to malloc is costly.
Yeah. But I mean, remember, create linked list is only ever going to be called once.
No, it's not.
Yes, it will be, because these blocks are only going to be created once.
But aren't you not gonna remove them eventually when we pop out?
You know what?
No, leave it for now.
No. Actually, you reminded me of a mistake. That's good. You did a good thing by reminding me to do this.
Oh, so someone's saying, why is your keyboard making a lot of noise?
It's the keyboard that I'm using.
The reply is actually good. It's a mechanical keyboard.
Yes.
Oh, I thought you'd be using your laptop keyboard, not another one.
Well, it's just more convenient to code with this.
It's also more convenient. Yeah.
Alright, so basically what's going to happen here, what this code is going to do,
Mm-hmm.
we're going to start off with a node, we're going to keep adding nodes to that linked list, and the last node is going to connect to the first node, so it's just going to keep going round and around. And what that's going to do is make it so that we can have a loop that keeps going around the linked list without having to manually go back to the beginning every time we hit the end, so that saves a branch overhead, so the CPU doesn't need to like branch. Yeah.
What we can do eventually, I'm not sure if we can. This is possible on the GPU, but can we not say that the weight of say this being true is like 99% false?
The weight of what?
Like, so a condition. So remember when we were doing LLVM, that we say that when we hit a condition that we check if this is 0 or not 0. We're assuming that this is 0, 99%.
Like tell it the branch weights?
Yeah.
You can probably do that and see. It's just, it's not, yeah.
You wanna do this in LLVM?
No.
I'm not sure if this is possible on the GPU. I'm not sure if they have
Probably
weights.
not. No, actually, sorry. GPUs don't even have branch predictors on them.
Oh, okay. Then it's not possible.
Yeah. I'm just gonna quickly test out my implementation here.
Okay.
And
you know, in theory, if we really want to do this, we can probably do the next one. Is that, or in the video, is that we just use Golang and call C directly, just to do the hash.
we will definitely take a look at that.
Yeah, you print out 10.
Well, if we want to return the start node. What? Oh, maybe it didn't save. Oh, I forgot to compile. Alright, nice. Good.
Okay.
So yeah, the linked list function works. So we now have a linked list. Now we're going to use that for a channel. So for that, I'm going to create a struct, and this time I can actually do it the easy way, because we don't need to refer to itself. So that's good. Also, I believe malloc is defined in this header, but we'll take a look at that later. So typed of struct channel. Within the channel, we want the data, so that would be the linked list node. But at the same time, we also want a mutex for the readers, so read mutex, and also a writes mutex. And for that, of course, we will need to include pthread.h. So we should have the two mutexes. And then if we want to insert into the channel, then we would have a function void insert, or insert to channel, and we would take a pointer to a channel, as well as the data that we want to feed into it, and we would just say basically for or we would say current node, actually, so linked list node current equals the channel data, but then we're going to have an infinite loop where we basically just say the last operation within it will be current equals current next, but that'll only happen if we say if current fresh is 1, then well, if it's 0 actually, then we do something and then we break, so we have to do something here. But we also want to make sure that we lock it, so we would do pthread mutex lock. Is that a function? Yes. And we want to lock the write mutex, and then we want to unlock it as we're leaving. So, see, this is the stuff that Go does for us.
Yes.
But then current index, basically just set that to the index passed to the function and make sure that we tell the channel that this is fresh, and then we're good to go.
You know the funny thing is, in theory, we could technically just get the C code that the Go team used. And
yeah, I don't want to adapt their C code for our use case. That would be even more difficult right now.
But it'll also be like in the early version of channels.
Yeah, but it's fine. Alright, so once again, we want to, in the read function, we want to lock the read mutex, and then we want to unlock it as we leave, of course, or else we could only ever read once. And then basically the same logic, we have the start of the linked list, and then loop infinitely, and for every index in the loop, at the end, if nothing, go to the next node in the chain. Otherwise, if we see something in the list that is fresh, then we want to, well, we can't return, let's just say index, and let's not initialize that here, and let's just do index equals current index, current fresh equals 0, and then break, and then return index. Okay, I feel like that would give us what we need it to do. Now, to test it out, what I'll do is I'll just create a global channel, and what I'll do from there is just have a little worker function, just to quickly test this. How much more time do we have? Okay, we have good time.
So we have enough time to just do the channels. We might not have enough time to actually implement the whole architect.
That's fine.
We can just review this next week.
Alright. So get from channel, and then just printf that, basically. And also, just to make sure that we don't get anything writing over anything, we're gonna have a print mutex, and I'm going to unlock and lock that at appropriate times. Then what I can do is within the main function, I can start off by initializing my channel and my mutex. So I'm going to create a small function called create channel, which will just allocate the memory for a channel, like so, malloc size of channel. And then from there, just set the channel data to a new linked list, and the length of the linked list is going to be passed over through this function. And the read mutex is going to have to be initialized, and the way I'm going to do that, it's not a pointer, is it? No, that's just a regular thing. So we would just set that to, how do we create a mutex? Let's see. Mutex. See, I'm forgetting the way you create a mutex. You do it by pthread mutex init. Okay, that makes sense. Just make sure I know what parameters we need to pass. Yep. Again, we're not doing error checking right now, but I can just pass a pointer. Oh, no, I don't want it to be that small. Okay, we can just pass a pointer and null, and also initialize the write mutex. Then within here I can say chan equals create channel, and the length should be like say 100 just to begin with, and then print mutex. Maybe we can just pthread mutex init, pass it a pointer, and null. Yeah, that looks good to me so far. And then just for int I equals 0, I less than, like, let's just say we want to spawn 5 threads, I plus plus. I made the same mistake as you there. And then we want to do pre-thread create, and of course we need to have a TID. Is that the valid type, or is that not it? I think it's pthread TID. I think so.
Okay.
Let's see. Is it? Where is it? Where is it? And tid. Where's tid? No, it's just pthread t. Not there. Then I can create it, pass it a pointer t, null, worker, null, and
This if it work.
I think that should be all. Oh wait, I need to also do for int I equals 0, I less than 100, I plus plus, write to channel, or what's the thing called, insert to channel, pass it the channel, pass it what I need to write, and I can also, just for the sake of keeping things clean, make this a 0. Alright. Now, if we compile and run, if we were able to compile, it would have worked. Looks like we need to pass it a pointer to the mutex to lock and unlock, which is something that I did not realize is a necessity. But apparently it is.
It also kind of makes sense.
Yeah, it does, but I didn't realize that. Okay. Okay, it compiled. Segmentation fault.
Nice.
Probably I mean, one thing that I can definitely tell is an issue is that needs to return and this needs to return. Okay. See, now in Swift that would have been an error, not a warning.
This is why we don't use C.
Okay, so now we need to do the pre-thread joins. Which...
Why do we need to do the join? It should be able to print out everything.
No, because before it's able to print out everything, it just exits.
Oh, yeah, I forgot about that. Can we now just make it sleep for like some time?
That's what we're gonna do.
10 milliseconds?
Sleep is by seconds. You sleep
is it?
Seconds. Yeah.
Oh, okay, sorry.
No worries.
I was assuming is wait, what?
Why we only printing at 5? Stuck at 4.
Oh, wait, you returning it right away. It's not a loop.
What?
Your worker is not a loop.
Ah, yes, that makes sense.
No. The Y at the very top.
Yeah, I got it. Or even just...
You and your go-to. There we go.
There we go. Yep, looks like we got everything in
49
order. 49 was at the very beginning, but yeah, that makes sense though because the 49 wasn't printed again.
I'm surprised that 49 was the one that like just jumped.
I mean, if we run it again, it'll probably be something else. 31 this time.
Okay, I guess there's mostly linear except for that one.
Yeah, because...
Can you remove the p mutex locks for the print?
Sure. It'll probably like print on top of each other, but we can try.
It shouldn't.
Really?
Well, I'm hoping it doesn't. I'm assuming.
Oh, it didn't. Nice.
Yeah, it should be fine. Now we see more of like a randomness.
Random, yeah, like a...
Yeah, because the other one was like way too like perfect. I'm like, that doesn't make sense.
Yeah, I feel like it was the print mutex that did that.
Yeah, I feel like what...
Go ahead.
I feel like what happened is that when we insert, we're always gonna insert 1, 2, 3, and so on. And and then on top of that, we only ever taking one back from the channel. So we're not really multi-threading.
Yeah.
But I'm surprised that only one number ever get messed up. Uh,
Yeah, that was weird. But anyhow, this works now. So here's what we're gonna do. Let's see if we have any questions. I see that we have only 5 minutes left, so we don't really have enough time to implement the rest of the C implementation of this algorithm because we can't do that in 5 minutes. But we will. So here's the plan for next week. We'll spend like the first quarter of next week's episode working on the implementation for so like finishing up the C implementation, and then we've got something really exciting planned that I'm sure you're gonna like. In the meanwhile, I will be releasing the video on how to do this on GPU. So if you'd like to figure out how to use CUDA to do something similar, do watch. I'll give you a bit of a sneak peek. We go from doing approximately 100 million to doing 8 billion per second. So that's gonna be really good.
and just as a reference, that's still pretty slow.
It's okay, yes, I agree. But to think that we can go from CPU, like even a power CPU, which is giving us 100 million currently, to eventually 8 billion per second. That I know that absolutely we can get a lot faster and we need a lot faster for blockchain, but still, pretty fun to see.
Let's see if there's any questions, and then from there we can just call it a day.
Sounds good. All right, so go ahead and let us know if you have any questions. I see that someone did mention that on Mac OS GCC is just an alias for Clang. That is right. And that's only though if you're using GCC from the Xcode tools. From the Xcode tools, if you type GCC, you'll literally just type alias to Clang. But if you actually install GCC separately, then of course you can run GCC on Mac. Now, you did also mention Semaphore. Yes, I would have preferred to use semaphores instead of mutexes here, but for some reason I was experimenting with pthread, not pthread, with system semaphores, and for some reason they were not blocking for me. So like when I would wait on the semaphore, it wouldn't block. I tried a super minimal example, it wouldn't work on Mac, I don't know why, so instead of using semaphores, I'm using mutexes. What else?
Maybe you can answer. Someone mentioned Clanage is the alias to GCC on Mac.
Yeah, that's what I just talked about.
Okay. I actually did not know that was actually the case on Mac.
Yeah, it is. It is.
Is it like something new or just
no? That's just always been like that.
Okay, makes sense since
you actually have the GCC tool installed, maybe because you have a dependency that needs it. But on most Macs, by default, when you install Xcode, you're not going to get GCC, but you'll have an alias that says GCC to Clang.
So you just have GCC.
I mean you have Clang. Better than GCC, so.
Okay. Right. I don't really see any other questions.
Neither do I. But yeah, go ahead and if you have any more questions, feel free. We still have like a minute more, but in the meanwhile, thank you very much everyone for joining in today. Once again, we got a Golang implementation where we have separate Go routines doing generation of random strings and separate threads actually doing the hashing itself. One thing that I noticed that was really interesting, which is just off the top of my head something that I really liked, is that before when we scaled from, I forget how many threads we scaled from, but we did increase the number of threads, but on Power, the number of threads that were actually running were still 130. So the Go runtime was actually handling them for us, while keeping the number of system threads constant, which is really fun to see.
The thing is in Golang is that you will never ever create more threads than the number of CPU threads there is. Unless you explicitly tell it to create a separate one for itself. So Golang will try to only ever spin up one thread per node per core if you require, and that's it. When I did some testing and made it so that each core, so each of those one-on cores was running on some chunk of CPU to see, like, try to offload it to certain areas. The one thing I noticed that I was spinning about almost 1,000 threads. And that was kind of hurting performance a little bit because there's a lot of context switching happening.
That makes sense. And the more you can reduce context switching, the better, because unlike on a GPU, on a CPU, context switching is very expensive. Relatively very expensive. And so we want to reduce that as much as possible.
And also another change that we did, and this is why CPU was a little bit faster. So like we went from 20, 30 million all the way to 100 million hashes per second. Is that we're not dependent on one chunk of memory anymore that having all the data. Each CPUs will have some some subsession of that data, because we spin up about what 140, no, not 140, 50 threads, and 50 of them will have blocks, so memory doesn't have to constantly reference the same area. And hopefully in L1 or L2 cache, we will save those numbers. And I'm pretty sure on the power system, everything was just in L3, because I believe they have enough cache.
Huge L3 cache. Like it has, I think, 4 kilobytes of L3 cache, which I mean we can actually check.
We might actually be saving a lot of the blocks in just L3 cache most of the time.
Most likely we are. I actually want to quickly see.
That was CPU?
How much? Yeah, we have 10 kilobytes of L3 cache.
Oh, that's actually a lot. That's actually enough to.
If the compiler is aware of that, then actually no, that's not a compiler thing. That's a CPU thing. So yeah, it should be storing the majority of this in cache.
Because every time it does a block, it usually load more than just that one area. So it might be able to load the next block in by itself.
Yeah. And what's interesting is that when we do the random number generation in separate Go routines, we're doing like latency hiding in a way where as the 3 other Go routines are doing the hashing, while that's happening, because the CPU is stalling for a bit, it's just waiting for that hashing to happen, in the meanwhile, we can go and generate more random numbers. And by the time that's done, we already have a block of new random strings that we can then use. And
I do wonder.
Of that, we have better performance.
Yeah, I also do wonder is that if we reduce the block size, are we able to get into L2 cache and keep it there for a while? Because
I wonder.
Because if we can get into L2 or even L1, we might be able to really like increase the performance. The main reason why. What?
Sorry. No, we have 10 megabytes of L3 cache, not kilobytes. I was confused.
I was just going where you were saying. Yeah, because.
And we have 32 kilobytes of L1.
Yeah, which I doubt we got in.
No, we're never going to get to L1.
Yeah, we were in L3 most of the time. And compared to your Mac, you don't have that much.
Definitely not.
I don't know how to check.
That's good. We will go ahead and next week, I see a question, will this be a blockchain? We will not be putting this exact implementation into a full blockchain, but do stay tuned for more content around blockchain very soon. I can't give you too many details just yet, but it's something that we're working on. Next week we'll be distributing this even further across more machines, and I'm sure that's going to be exciting to see. And so thank you very much, Omer, for joining and helping me out with today's implementation. I see you're no longer using your signature space background, but anyhow. Right, thank you for joining in. Thank you very much, everyone, for joining the live stream. We'll see you next week. Once again, if you want to be notified when we're doing the live stream, make sure to subscribe and hit the notification bell. That way you know when we're actually streaming. And once again, thank you very much, Omer, and thank you for joining today.
Bye, guys. Bye, Tammy.
Bye-bye.